Good morning, everybody. Welcome to another exciting morning of chemistry with your host, me, Dr. White. Now, thank you, Andrew. And a couple of things I'd like to announce. One is next Tuesday, do the problem set before then. I'll be going through the problem set for I believe it's chapter 8. That's the stuff on what I'm doing now on the multiple step grams to moles, moles to gram, actually mass with balanced chemical equations. The following Thursday, it will be due, and I'll also go through the problem set, balanced chemical equations. Remember my 3 tips when you balance chemical equations, and I'll tell you that later because that's today's lab also. All right. The other good news is we're ahead of schedule, which is always good because I don't have to rush. If you notice, I've been taking my time because I've taught this class before, number of times before. And this is actually the second time I'm teaching it online like this. So I think I've got it down pat, I hope. Now, I found out yesterday, and it hasn't been published uh, officially, but it will be in a week or so. Next semester, first of all, COD is going to be online again. I will be teaching the same course, actually 2 sections together, uh, and it's VCM 01 and VCM 02. So if you know any students you don't like and you want them to suffer through me, actually, if you think they want to take my class, I'm available. As you know, my classes fill up real quick. Uh, this class, I found out after they had already had other people posted for it, they switched my class to this section that didn't have a teacher and only had one student. Within 3 days, I had 10 people waiting. It filled up. I guess people know about me. Maybe it's ratemyprofessor.com or word of mouth or all the above. All right, let's get to work. I apologize that yesterday I didn't send out an email. My back was telling me don't do anything, and I didn't much. And but today I'd like to go through chapter 6 problem set. If you haven't done it, I'd highly recommend you do it. Shh, let me, don't tell anybody, but take a deep breath and relax. Test 2 is the hardest test of the semester, hardest in terms of low scores or average. However, this last semester and a couple summers ago, I had a class, each case, which it wasn't the lowest. But what that means is you really have to do your practice problems now. Don't wait for a day or two before the test, because this is a harder test than test 1, because there's more material and it's more complex. But if you do the practice problems, you'll do okay. Actually, you do more than okay, you'll do real good, but you got to do that. Everybody see my chapter 6 practice problems on the screen? Good. Let's go through it. Things you should know. You should know what is a mole. A mole is the chemist's counting unit, or you can say a mole equals Avogadro's number, which I asked the next thing you should know, or it's equal to uh, the atomic weight of an element, or it's also equal to the molecular weight of a compound. So there are many definitions of a mole. I put down the first one I taught you, and that was a counting unit the chemists used. Next, what is Avogadro's number? Key number you should know, and that is Avogadro's number is 6.02 times 10 to the 23rd, which reminds me, remember, my birthday is the end of December, and all I want for my birthday gift, is a mole of pennies. By the way, if you do the math, that's 100 million piles. Each pile is $1 billion in pennies. But if you want to give me a certified check, I'd take that too, as long as it's a mole of pennies. All right. Now, before I move on, if I find the right slide, if you, let me ask, because I was playing, everybody see 1 mole equals an element on the screen? You see that? Okay, thank you. All right, this is from the file that's in the lecture section of Blackboard called Important Information Test Number 2. And as you see on the page, besides other things here, which we talked about, I will give you the following, which you should know how to use. In the past, I asked students to memorize this. Now, I learned about 1.5 years ago, it's almost 2 years now. It's better for me just to test your chemistry knowledge, not how good your memory is under pressure. And you should know how to use, and we're going to go through this, 1 mole of an element equals Avogadro's number of atoms of that element. 1 mole of a compound equals Avogadro's number molecules of that compound. Also, 1 mole of an element equals the atomic weight of an element, and 1 mole of a compound equals the molecular weight of a compound, and sometimes called the formula weight. I like molecular weight myself personally better, so I use it. And the molecular weight is the sum of all atomic weights. This you'll be given, but you have to know how to use it. Oh, I got to do this. You know it's coming. And you need to know how to use your good buddy, your good friend. Oh, that was a long one. Unit analysis. Truthfully, it's been my good buddy and my good friend for many, lot more many, Avogadro's number, many years. So let's go start using it. Oh, let's go to the high rent district, number 4. And remember, there's no such thing as a dumb question. If you want me to go over something on this problem set, I'll do 1 page at a time. Or if you have any questions, always remember, there's no such thing as a dumb question in my class, in my life. All right, number 4, how many atoms are in 1.23 times 10 to the 5th moles of gold? When you do it, and these are called relaxed word problems because you're given information and questions in words. And you're asked, what are you asked to find? Well, I like to define that. Atoms of gold, AU is gold. What are you given? How many moles of gold? You start and put what you're given. You come over here. What units do you want your answer? Whatever your answer units go on top of a ratio. Whatever you're trying to get rid of, go underneath. Remember, anything divided by itself becomes the number 1. So this cancels out. One of these days, I'll figure out how to write it with my whiteboard or tablet on a PDF file, but I've read online, it's pretty much impossible at this point, but you can see my marker moving or cursor. This is 3 significant figures. Avogadro's 3 significant figures. 1 is part of the definition, 1 mole. That's an exact number. My answer, 3 significant figures. Now, I know a lot of teachers make students memorize. For this type of problem, it's this. For this type of problem, use this ratio. You don't, if you know your good buddy, oh, I got to do it again. Your good friend, unit analysis. And if we look at Number 6, how many moles of sulfur are in 1.01 times 10 to the 45th atoms of sulfur? Well, what do? You find out, what are you being asked to find? Moles of sulfur. What are you given? How many atoms of sulfur? This is the only thing you have to start with. You're trying to get the moles of sulfur. In case you forgot, S is the chemical symbol for sulfur. And we'd say what you're using, your good buddy, your good friend. I am not going to use the whistle again for a while. You'll get whistle poisoning, and I don't want that to happen. But here, what you're trying to get to goes on top of the ratio. What you're trying to get rid of goes underneath. Where do you get these numbers? 1 mole equals Avogadro's number of atoms of any element. If you look on the screen, this will be given to you in test number 2, important information, but you have to know how to use 1 mole equals Avogadro's number of that element. And that's why I have practice problems. So this is where we get these numbers. 1 mole equals Avogadro's number. Actually, I'm on the wrong problem. 1 mole equals Avogadro's number. It's still the same thing. And now, if I look, atoms of sulfur divides by atoms of sulfur gone. I'm left with the right units. I do the math, 3 significant, 3 exact number, 3 significant figures. Now, let's look at number 7. How many molecules are in 23.45 moles of water? What are we trying to find? Molecules of water. What did I just do? Drink some water. Uh-oh, it's Bad Humor Thursday. Even with my bad back, I can still knock out bad humor. Am I impressive or not? Not. But anyways, what are you trying to find? Molecules of water. What are you given? 23.45 moles of water. Use unit analysis. How? What you have, you start with. If I'm look at my answer after the equal sign of some math operation, what units do I want? Molecules of water. If I can do this in one ratio conversion, whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes under here on the bottom. Remember, moles divided by moles of water equal 1. It cancels out, and I'm left with molecules of water. Where do I get the numbers in the ratio? 1 mole equals molecules, Avogadro's number. You'll see that in the important information. 4 significant figures, 3. Remember, Avogadro's number is not an exact number. It's calculated, and the one I use and most chemists use for the calculations is 3 significant figures. And 1 is an exact, so my answer is 3 significant figures. Any questions on going from moles to atoms, atoms to moles, or I like the fancy demonstration here, or moles to molecules or molecules to moles? Any question? Going once, going twice. Let's move on. For those of you here, I don't think I've ever put on a test too, where you go from an element weight to moles or moles to weight. So I'm going to skip these 2, even though it's good to know. But I do molecules, so let's look. Oh, I gave away a secret of Dr. White. Shucks. But anyways, first of all, let's talk about molecular weight. If you go to test 2, important information, I used to make students memorize this, but you don't have to, because it tells you the molecular weight of a compound is the sum of all atomic weights. And what's the molecular weight of water? Well, water is H2O. I would give it to you, but I hope by now all of you know that. And it has 2 hydrogens, 1 oxygen. On test number 2, it will say under your name, please use proper significant figures for all calculated answers. And it will say, please round off all atomic weights to 3 significant figures. Hold on, because I forgot to open up my periodic table. If you look at the periodic table, let's remember hydrogen is 1.008. How do you round that off to 3 significant figures? Keep the 1, keep the 0, keep the 0. That's my 3. 8, is that 4 or less, or 5 or higher? And time's up. It's 5 or higher, so I drop the 8, increase the 0 to 1. So for hydrogen, 3 significant figures, atomic weight is 101. If we go over to oxygen, I'm going to let you try this one. 15.9999. Round that off to 3 significant figures. Go. All right, let's take a look at this. If we look at this, we keep the 1, keep the 5, keep the 9. That's my 3 significant figures. The 1 we round off after the first 9 is another 9. That's 5 or higher. I think you all know that. So that 9, the other we drop, we increase this by 1. That becomes 1.0. Therefore, this becomes 16.0. Somebody, you can't see, says the screen. I should have done my thumbs up, people. Can you see the periodic table now? Okay, thank you. All right, let's do another one. Why don't you round off carbon to 3 significant figures? We don't do it for the needed for the problem we're doing, but guess what? It's good practice. All right, time's up. How do you round this off to 3 significant figures? And let's do it. Keep the 1, keep the 12, keep the 0. The number used to round off is 1. Is that 4 or less? Yes. And therefore, you take and drop this and everything else. So for carbon to 3 significant figures, it's 12.0. Let's go back to our problems. Actually, I forgot. All right, everybody see the problem set? Thank you. All my thumbs up people, I appreciate it. Zoom has problems. So let's see. We're right here. 2 hydrogens, 1 oxygen. We figured out from our periodic table, atomic weight, the 3 significant figures, a hydrogen is 101, oxygen 16.0. This times 2, remember 1 and 2 are exact numbers, 202, 16.0. You add them up. Now, listen carefully. When you do addition, you have the same number of significant figures to the right of the decimal point, right here, as the number you're adding that has the fewest. The first number, 202, has 2 past the decimal, 16.0 has 1 past the decimal. Therefore, you round this off to 1 past the decimal, keep the 0. This 2 is 4 or less, so I drop it. Everything to the left, you don't ever round off in addition. It took me a while to acknowledge that's right, because at first it didn't sound right, but it is. So the answer is 18.0. Let's do another one. What's the molecular weight of H2SO4? By the way, this is sulfuric acid, and if my memory serves me correct, which it usually does, this is the molecule that's made the most of any compound in the United States or even in the world. This is heavily used in industry, chemical industry, and others. So there are more tons of sulfuric acid made in the United States than any other chemical. But what's its molecular weight? Well, from the formula, we have 2 hydrogens, 1 sulfur, 4 oxygens. Hydrogen, the atomic weight, the 3 significant figures, is this number. There's 1 of sulfur. If you round it off, you get 32.1. And I forgot the bracket here, but for oxygen is 16.0. And I forgot the equal signs. Oh, it must have been the mess up my problem virus that got here. But anyways, I shouldn't really joke about viruses considering what's happening in our society today, but what the hell? It's a different type of virus. We have 2 times 101, 202. 1 times 32 times 32.1, 32.1. 4 times 16.0, 64.0. Add them up. There shouldn't be that extra dot there. I don't know how it got stuck in there, but 2 past the decimal, 1, 1. Round this off. Past the decimal to the right is 98.12. So keep the 1. 2 is less than 4 or less. Drop it, and the correct answer is 98.1. All right, let's use this. And even on the problem set, 1 mole of a compound equals the molecular weight in grams of that compound. Now, question is, how many moles are 34.56 grams of water? Well, what do? Look at the problem and say first, what am I being asked to find? Moles of water. How many moles? What are you given? The weight of the water. This is the only number we have to start with. What do we want our units to be in of the final answer? Moles of water. Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of our ratio to convert grams to moles. And whatever we're trying to get rid of goes underneath the ratio, grams of water. Now, where do we find a relationship of moles to grams of water? 1 mole of a compound water equals its molecular weight, water, in grams. The molecular weight of water, which we just did, but I'll go through it again quickly. 2 hydrogen, 1 oxygen, atomic weight, 3 significant figures, hydrogen, 101. That should be a 1. I don't know how I messed up on that, but Dr. White makes mistakes too. And 16.0, don't look. But anyways, add it up, you get 18.0. And now you do the math. Before you do that, grams divided by grams of water comes number one. I'm left with moles, 4 significant, 3, 1. And the answer is 1.923 significant figures. Let's look at my mistake here. Say you made a mistake on the molecular weight. And that happens. If you don't show your work and just put an answer and it's wrong, if it were wrong, in this case, it still would be right, but if it were wrong, I'd give you 0 points. If this were like a 5 or 6 point problem, and I look at it and I say, if you showed your work, oh, you put the wrong number here. Ah, that's a simple mistake. I'll only take off 1 point. So it pays to show your work on my test. And by the way, since I don't use multiple choice tests, that's why it's even more important to show your work. All right, let's do one more and see if I got this right. And keep my fingers crossed. How many moles are 2.345 grams of ammonia, NH3? What are we being asked to find? Moles of ammonia. What are you given? The weight of ammonia, 2.345 grams. This is all we have to start with. What do I want my answer to be in units? Moles of ammonia. If I had a ratio, how do I know what goes on top of this ratio? What you're trying to get to goes on top, moles of ammonia. I don't want grams of ammonia in my final answer, so I put that underneath. Where do I get the relationship of moles to grams of a compound? It's not important information, test number 2, but it's also written on top of the page. 1 mole of a compound equals its molecular weight of a compound. Important information. It also tells you molecular weight of a compound is the sum of all atomic weights. So if we come down here, where do we get these numbers? 1 mole equals the molecular weight. The molecular weight, and I got it right down here, is 3 hydrogens, 1 nitrogen, the sum of all atomic weights. Each hydrogen to 3 significant figures is 1.01. The 1 nitrogen is 14.0. Do the math, add it up, you got 17.03. Now, what do? You say, when I do addition, I get the same number of significant figures to the right of the decimal, past the decimal, as the number that has the fewest. This has 2, 0 and 3. This has 1, a 0. What's lower, 1, 0, 1 or 2? 1. So round this off to 1 past the decimal. Keep the 0, that's my 1. I use this number 3 to round off. Is that 4 or less? Yes, so I drop it, 17.0. And now I know that 1 mole of ammonia is 17.0 grams. Do the math, 4 significant, 3 exact number. Here's the number you get. Now, a lot of you will have your calculator in scientific notation, but for this problem you don't. And on a test, if you wrote it this way or this way, either one, actually both, would be correct. Did I tell you I'm this close to the person who's grading the test? Me. All right. Ooh, let's do 17 and 18 are the same. Let's do 18 because we've had enough salt in our diet. Oh, that was awful. Just think, you're paying to hear all this awful humor. I'm getting paid to dish it out. That was pretty awful. But anyways, back to the problem. 18, 6 or 8 points. How many grams are 56.1 moles of KOH. KOH, potassium hydroxide, also an important chemical used in the United States. And therefore, what are we being asked to find? Grams of KOH. What are we given? How many moles of KOH do we have? And what do? I start with the moles. What answer do I want what units do I want my answer in? Grams of KOH. Now I use my good buddy, and truthfully, my good friend, unit analysis, and I say whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. Moles divided by moles cancel out. I'm left with grams of KOH. That's always an important check. The students sometimes get this upside down, and you see moles times moles divided by grams. Nothing cancels out. You know, oops, I better go back and check what I did wrong. Here we didn't. Now, where do I get the relationship for the numbers that when you do it, you won't have there? You got to fill in 1 mole of a compound equals its molecular weight in grams. The molecular weight is the sum of all atomic weights. When we come down here, what's the molecular weight of KOH? Because I need it to fill in that number, 1 potassium, and it's 39.0. It disappeared from the screen. Sorry about that. 1 oxygen, 16.0 is the atomic number for oxygen. 1 hydrogen, 1.01. Add it up, you get 56.11. Remember, when you're doing addition, you get the same number of significant figures past the decimal as the number that has the fewest significant figures past the decimal. And if we look here, we have 1, 1, 2, lowest number is 1. How do you round this off to 1 past the decimal? Keep the 1, second 1 I used to round off. That's, oh, look, it's 4 or less. Yes, it is. And therefore you drop it, and it's 56.1, 3 significant figures, 3. And I use scientific notation. If you didn't, you could have written it out, but I would rather you do this way because there's less chance you make a mistake. But it's 3.15 times 10 to the third grams of KOH. And if you haven't figured it out by now, Dr. White likes repetition and overkill. Let's remember again, this is important information of test number 2. This is given to you, but you should know how to use it using your good friend, your good buddy, unit analysis. 1 mole of an element equals Avogadro of atoms of that element. 1 mole of a compound equals Avogadro's number of molecules of that compound. 1 mole of an element equals the atomic weight of that element, and 1 mole of a compound equals the molecular weight of that compound in grams. Remember, the molecular weight is the sum of all atomic weights. Any questions on that? Going once, twice. All right, we're doing stuff on Tuesday, and I like to do a quick review to remind you of something important. And let's have a simple balanced chemical equation for hydrogen, two oxygen, two oxygen. It's balanced. All right, everybody see the problem on the screen? I'm glad I asked. Now do you see it? Thank you. All right, why don't you try this one out yourself first? How many moles oxygen are needed to make 1.475 times 10 squared moles of water? Remember the coefficients, the number in front of an element or molecule in a balanced chemical equations give you molar relationships. And this tells you 2 moles of water, of hydrogen, 1 mole of oxygen makes 2 moles of water. 2 moles hydrogen, when there's no number, it's 1 mole oxygen makes 2 moles of water. Your turn. Use your good buddy, your good friend, your analysis. And when you're done, give me a thumbs up. Again, when you're done, give me a thumbs up. But take your time. Don't rush. On my account, get done quicker. No, take your time. You don't have to calculate molecular weight for this one. All right, anybody need more time? Going once, going twice. Let's do this. All right, first thing you should do, ask yourself, what am I being asked to find? And the answer is, how many moles of oxygen? What are you given? Moles of water. And the only number I have to use is this, so I'm going to use it. If there was some magic conversion, what units do I want my answer in? Well, it tells you right here, because you figured that out. Moles O2. Now, use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. And on top, I want moles of O2. Underneath, I want moles of H2. And where do we get these numbers? From the balanced chemical equation. When there's no coefficient, the number is 1. So this tells me for every 1 mole of oxygen, I make 2 moles of water. For every 1 mole of oxygen, I make 2 moles of water. These are exact numbers. And now it's time for first to write the number down so I don't forget it, because I do these questions on the fly. And this one I could probably do in my head, but I'm not going to take a chance today. And you all should see my spreadsheet. Everybody see the spreadsheet now? Nope. Zoom tells me you should be. Now do you see it? Thank you. It's the one bug in Zoom. I'm going to have to find how to. So I put in my numbers, calculate it, and this is what my calculator gives me. Now, if we go back and look at our calculation, this is 4 significant figures. This is exact number 1, exact number is 2, because the numbers from a balanced chemical equation, molar ratio, are exact numbers. So my answer should have 4 significant figures. And how do I round this off? Keep the 7, keep the 3, keep this 7, keep this 5, use the 0 to round off, and the answer would be it's less 4 or less. So I drop all that, and that would be 7.375 times 10 to the 1 power. On this one, if you put 73.75, that would also be correct. Let me rewrite that. And that's your answer. And that's how you do these type of problems. And I wanted to review this because we'll be using it after the break for the three-part problem. Remember, the coefficients, that's the number in front of the molecules of a balanced chemical equation. When there's no number, it's 1. Those numbers tell you molar relationships. 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. And I think I'm going to stop a minute early, come back at 10:55. I'm going to turn off my screen and my microphone so you don't hear me going, oh, it hurts when I stand up. Hopefully it won't. With that, I'll see you at 10:55. Take a break. I need one. All right, good news. I'm back and I'm still alive. Everybody, it's time to get going. Uh, my back is in better condition than it was yesterday, which tells me it's healing. But thank God for my heating pad. I've had this heating pad, I'm come to think of it, at least 25 years, and it still works like a champ. Keep on working. All right. Thank you, Diana. I feel due. Actually, I am. Uh, Years ago, playing tennis, because I didn't know how to stretch properly, I ripped my calf muscle on my right leg. And boy, that was bad. And I know I didn't rip any muscles because I know what it feels like when you rip a muscle, but I sure stretched the heck out of them. And ibuprofen, stretching, and relaxing. In my laser boy, I have a laser boy. I've had a number of them for the last 30 years. If you don't own a laser boy, go out and buy one. The rocker recliner, they're the best. But you didn't come here to hear how what I do. You came for chemistry, so let's do some. And let's look at the following problem. And I'll ask my thumbs up people. Do you see the problem on the board? Thank you. All right, I'll do this one. You know I'm going to share with you so you can have some fun too. And that is, let's look at the question. How many grams of ammonia, NH3, are made when you react 4.76 grams of hydrogen with an excess of nitrogen? So what are we being asked to find? Grams of ammonia. What are we given? And we're also given a balanced chemical equation. You need that to do this problem. Now, there's no way I can go directly from grams of ammonia or grams of hydrogen to grams of ammonia. You can't. There's just no way. Trust my word, I'm a chemist. I know these things, but you can't. So let me show you from important information. It's also in the chapter slides. Everybody see that on the screen? Mass calculations. Can you see that? Okay. And what we mean by mass is grams. And there are 3 steps. First step, whatever you're given the weight of, you convert to moles. Second step, and this will be given to you. A long time ago, I used to make students memorize this. I don't now. Once whatever you got into moles A, you convert to moles of B. And finally, your final answer you want in weight. So the moles of B you just found, you convert to mass of B, which we just did. So let's take a look at this. Everybody, you see the problem on your screen? Good. So how do we begin? Step one. So from the instructions I just read, whatever you're given in grams, you convert to moles. Well, what do we have in grams? We have 4.876 grams of hydrogen. And we want to get to moles of hydrogen. And how do you do that? I'm going to let you just try and figure out what goes on top and what goes beneath the ratio here and here. I'll give you 10.8 seconds. Go. Not numbers, just the units. Time's up. Use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. And therefore, you should be able to put in moles of hydrogen, grams of hydrogen. And remember, 1 mole of a compound equals its molecular weight. So the molecular weight of hydrogen gas is 2 hydrogen, sum of all atomic weights. I know this by heart, but you may not. And you should know how to know that the atomic weight to 3 significant figures, look on the periodic table, for hydrogen is this times that. 2 is an exact number, 2.02. So for every 1 mole of hydrogen gas, H2 is 2.02 grams. Now, before I go any further, grams of hydrogen divided by grams. Remember, anything divided by itself equals the number 1. And therefore, it's time to go to my calculator. It's time to go back because I forgot to write down. Hang on. And everybody see the spreadsheet? Thank you. So I'm going to do this, 4.876. You want to keep it in scientific notation. You could have, I just thought I'd do this. And you get this number. Now, I had 4.876, 4 significant figures, 202, 2.02, 3. And now round this off to 3 significant figures. Keep the 2, keep the 4, keep the 1. Forget about the zeros because my spreadsheet pops them in. Now, there's 2 ways of using significant figures for this type of calculation. One is round off at each step, which Dr. White likes to do, or wait till the end. I'm a round off at each step, but if you want to wait till the end, you can now calculate it both ways. And on certain questions on tests, there might be two different answers. So now we've done step 1, and now we're going to go to step number 2. Again, this is given to you. Now we have moles of A to go to moles of B. And what does that mean? Well, we just calculated A, moles of hydrogen. And if we look back up here, what are we trying to get to? Grams of ammonia. But first we need moles of ammonia. That's our B. So what we're trying to do is go to moles of NH3. And this we already have 2.41 moles hydrogen. And if we can convert this in one step, you can. We have moles of hydrogen. We want to go to moles of ammonia. And I'm going to let you first figure out what units go on top, what units go on bottom, not the number, what units. Your turn. Time's up. Use your good buddy, your good friend, your analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And now I know on top I want moles of ammonia. Underneath I want moles of hydrogen. Where do I get these numbers? Well, you look at the balanced chemical equation. And this tells you for every 1 mole of nitrogen, notice you see here in the problem excess. As soon as you see excess of something, you know, ignore it, and I will. But it still tells me every 1 mole of nitrogen reacts with 2 moles of hydrogen. And actually, I made a mistake. This should be 3. Hold on. Now it's balanced. Shh, don't tell anybody I made a mistake today. All right, for every 3 moles of hydrogen, I make 2 moles of ammonia. For every 3 moles of hydrogen, I make 2 moles of ammonia. And that's where I come down here. For every 3 moles of hydrogen, I make 2 moles of ammonia. Let's see if I did that right. I did. And that's where you get those numbers. Remember, these are exact numbers. And therefore, I can now go, no, I'm not going to go yet. I'm going to check, do my units cancel out? Notice I have moles of hydrogen divided by moles of hydrogen. Anything divided by itself equals the number 1. This cancels out. I'm left with moles of ammonia, which is what I want. And now I'm going to go to my calculator, otherwise known as my spreadsheet, and say this number times 2 divided by 3. I'll get this. I'll come over here and do the same thing. And this one, I'm going to round off to 3 significant figures. This side in column A, I'll wait till the end. And this would be 1.61 moles of ammonia. And that's 1.61 moles of ammonia. Am I done? No, because I'm trying to get the grams of ammonia. But I have moles of ammonia, and I'm in a good spot now to do step number 3, moles of B. In this case, B is now ammonia, to grams of B. So what that really says is I'm trying to find grams of ammonia, and I have 1.61 moles of ammonia. Guess what? I'm going to let you try and set this up and do this step yourself, because I want to share. Nitrogen has atomic weight of 14.0. Hydrogen has atomic weight, the 3 significant figures, of 1.01. Your turn. And when you're done, give me a thumbs up. All right, anybody need any more time? Anybody need more time? Going once, twice? All right, let's do this. Now, what do we have to work with? From up here, step 2, and also I rewrote it here, we have 1.61 moles of ammonia. We want to go to what? Grams of ammonia, which is grams of B. I use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. And once I know that, I'll put these in there. Grams of ammonia, moles of ammonia. And where do we get that information? Important information for test number. Oh, wrong thing. Important information for test number 2. It tells you 1 mole of a compound equals its molecular weight in grams of the compound. So if I have 1 here, what do I need to put in there? The molecular weight of ammonia. And how do I do that? I have 1 nitrogen, NH3, 3 hydrogens, 1 times 14.0, and this is 3 times 1.01. Do the math. 1 and 3 are exact numbers. Add them up. Hold on. I was already getting ahead of myself. Add them up. You get this number, and you have to round it off. Remember, when you add, you get the same number of significant figures to the right of the decimal point as the number that has the fewest. This has 1, this has 2, which is the lower number, and times up. Hopefully you pick 1. Keep the 0. Use the 3 to round off. It's 4 or less. So the correct answer, 17.0. Notice 3 significant, 3. Dr. White gets in that rut sometimes. And now I'll go to my calculator. No, I won't. I'm going to check here. Moles of ammonia divided by moles of ammonia. Anything divided by itself equals 1 because it cancels out. And I'm left with my right answers. And that's a check you should always do before you pick up your calculator. And here, you want to round them off to 3 significant figures, each of these. This one, keep the 2, keep the 7, keep the 3. 5 is 5 or greater, so this would be 27.4. If I come over here, round this off to 3 significant figures, keep the 2, keep the 7, keep the 3. 7 is 5 or greater. That rounds off to 27.4. It doesn't always, but in this case it does. And your final answer for this problem is this number. And that's how you do it. Remember, you have to use 3 steps. The first step, what did I do? I started with whatever I was given in grams, in this case hydrogen, I converted it to moles. And we did it this way, which you've done already. You did in the practice problems. And remember, 1 mole of a compound equals its molecular weight. Step 2, I had to convert what I just figured out in moles, in this case hydrogen, to moles of what I'm trying to get to, ammonia. And where do we get the numbers here? You come up to your now properly balanced chemical equation, and we want the relationship between moles of hydrogen and moles of ammonia. You look at the coefficients, and that tells you 3 moles of hydrogen make 2 moles of ammonia. And that's where I have the numbers. I now have moles of ammonia, but don't get too dizzy me going up and down the slide. That was awful. But it's awful Thursday humor. What do you expect? And here you're trying to get the grams of ammonia. So now we have to do step 3. Whatever you just figured in moles, you convert to grams. How do you do that? Here's the moles. We'll go to grams, use unit analysis again. Grams go on top, moles go underneath. And now, where do you get those numbers? 1 mole equals the molecular weight of ammonia. You add the sum of atomic weights, do the math, and that's how you do it. Now, one of the questions you should always ask is, what good is this? Why am I learning this stuff? Well, it's for you to understand chemistry. The actual reason why, what good is this, is you want to get a good grade in this class so you can get into a program or school for your future career path. But why learn this? Where do we use this in chemistry? Hang in there while I open something up. Hold on 1 second. I gotta close something down. There we go. Oh, look, there's someone you know, me. I'm in a chemical plant. This one happens to be in Louisville, Kentucky. If you look right here, and I'll talk more about this later on, this is a reactor. Think of it like at home, you have a pot or pan you do your cooking in. This is a reactor. It's 2 stories high. That reactor is where we do chemical reactions to make things. In this company, we're making resin, which is a fancy name for glue. And for my area, we made resins that hold sand together to make the molds to make your car engines and other things. Like if you look on your street, you'll see the metal tops or covers for sewers and storm grates. Those are also made in foundries. But our biggest customers were automobile companies. I worked with Ford, GM, and back then Chrysler. And this was huge. I'm about 6 foot, or right now 5'12". And you can see this is just the very little bottom of this. How many of you are familiar with the vehicles that deliver gasoline to gas stations? They're called tank wagons. I see you're all giving me that. Tank wagons are standardized. They hold 40,000 pounds, 5,000 gallons. That reactor that I was standing by, the normal operating amount of chemicals you could put in there is 160,000 pounds. That's four, yes, four tank wagons. That's a lot of chemicals. It's a lot of money too. At $1 a pound, that's $160,000 on one reaction. When I did the same kind of calculations, how much of this and this should I add to make how much I need to make, I'm dealing with almost, a lot of money. And I would do the calculation just like you saw. And then I would give myself enough time because part of my responsibility was at more than one company, the right to procedures. Also, some companies called recipes. I didn't like that, I like procedures better, to determine how much chemicals you mix together to make the product, how much product. And I would do my calculations, write them on a piece of paper, put them down in a folder. 3 days later, I'd always wait at least 2 or 3 days later, I'd redo the calculations from the start fresh and check, were my two answers the same? They always were because I took my time and I used my good buddy, my good friend unit analysis. And I knew I'm not going to make a mistake. I never did. I know one person who did one and he got fired because he blew $160,000, $200,000. Companies don't like when you blow that things when you shouldn't. All right, let's move on. We've done this. Remember, 1 mole of A equals molecular weight. The coefficient tells you molar quantities or ratios. And we did this already. Oh, wait, actually, we haven't. All right. The book has it one way. I like it another way. Dr. White has a Freudian slip. Sometimes I accidentally call that limiting reagents. It really should be reactants, and I got it right this time. Now, let's look at the following. Say I own a company that makes these pens, and I buy from someone else the cap. And I also buy from someone else the body of the pen. And what I do is I put the two together and I sell it as a pen. Now, what if I had 10 caps and 5 pen bodies? How many total units could I make? If I had 10 of these, but only 5 of these, after 5, I'd be done because I'd have extra caps, but I wouldn't have any more pen bodies. So I could only sell 5 of these. And that's the concept behind limiting reactants. Oh, I got it right that time instead of 70 reagents. But anyways, and this, let's go through a problem. First of all, in a reaction, sometimes you don't have enough of each reactant. And when one is totally used up, you can't go any further. Just like with the pen and the caps, the pen body. Now, usually you have one reactant that's in excess of the other. And let's see how to do this. All right, can everybody see the screen right now? Where I have balanced chemical equation? Good, thank you. All right, 5 to 6 points, depending on my mood when I write the test, which I probably are going to do this weekend. I have a balanced chemical equation, and the word part is how many moles of water are produced, are made, if I react 3.75 moles of hydrogen with 1.61 moles of oxygen. So the first question is, what are you trying to find? Moles of water. What are you given? This amount of hydrogen and this amount of oxygen. Well, what do? This is a limiting reactant problem. And if you go, and I didn't have it on my slide, but I put it in important information, which has disappeared. I got to open it again. Hold on. Everybody see limiting reactants on the screen? Thank you. All right. Here, what do? First, you determine the number of moles of product made using or produced using moles of each reactant. The lower number is your answer. Again, there's another way of doing this, but a student years ago showed me this was an easier way, and I use it. I also give that student credit. Determine the number of moles of product produced for each reactant. You got to do 2 equations or set up 2 calculations, and then the lower number of those 2 is the answer. So let's see how we do that. So I have to do 2 equations. One, I want to find out for each reactant, and I'll start with hydrogen. If I have these many moles of hydrogen, how many moles, what are we trying to make? Water. And I'll let you figure out what goes on top here and there, including the number, and you try that now on your own. Time's up. Use your good buddy. Unit analysis, whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath. And where do I get those? Well, first I'll put that in. Moles of water, moles of hydrogen. Where do I get that? 2 moles of water of hydrogen make 2 moles of water. This one I don't even have to get my calculator on because these are exact numbers that cancel out, and I get 3.75 moles of water produced. But here for limiting reactants, you need to do 2 equations. Each reactant, how many moles of product will you make? In this case, I have 1.61 moles of oxygen times something to get to what's the product, moles of water. And now I'll let you again figure out what goes on top and bottom, number. Time's up. Use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. Moles of water on top, moles of O2 go underneath. Where do I get those numbers? Right here. For every 1 mole, remember when there's no number here, it's the number 1. Ooh, that's a pretty looking 1. For every 1 mole of oxygen, how many moles of water do I make? 2. And if I do this math in my head, hopefully I did this right. Let me find out. .22. Let's see if I did it right. And I did. So how do you know what the answer is? Your answer for this problem, whichever one at calculation 1 or 2 is lower, is your answer. And therefore, the correct answer is 3.22 moles of water. Now, again, let me remind you, when you're trying to figure out how many moles of a product you're making, when you have a certain amount of each reactant, you have to figure out 2 equations, how much of each for each reactant, how much product that would make. And then the lower number is your answer. And that's how you do it. Now, this one will be on test number 2. So, but if I look at the clock, what I like to do is let's start the lab because my back is telling me, you know, you should get up soon. And I'm still alive. Yay. But let's go do our lab. Hang in there. It's hiding from me today. I got it. All right. Also finding out you can only have so much open on your computer before Zoom gets upset. All right. Last time today, thumbs up, people. You see the balanced chemical equation lab on the screen? Thank you. All right. Today's lab, you're going to be practicing balanced chemical equations. And you'll submit these pages where you put down the numbers where they're balanced. Now, this I got from the internet, so I think 2 of these are at least balanced. I'll never do that on a test, but on here you have. Remember, you get the same number of atoms on each side of the chemical equation, and you can only adjust the numbers in front, the coefficients, not the actual chemical formula. Now we see S, which is solid, G, gas, and I think there might be one with liquid. There is L, liquid. Ignore those letters. Now, let me remind you of the things I taught you already. For balancing chemical equations, 1, leave hydrogen, oxygen last. 2, remember if you have an even and odd of an element, multiply the 2 numbers and then you can have them. And I'll show you an example. I'll give you one I'll do from there. And don't forget, show your work underneath for you. You don't have to do it on a test, but make sure everything balances out. All right, everybody see the equation problem set 1 on the screen?
No.
I'm glad I asked, because Zoom tells me you should. Now do you see it? All right. Let's look at B. I'm going to do this one. So that means every one of you better get it right on the lab. So I'm doing it for you. Now, 1 aluminum, 1 aluminum. That's good. 2 chlorine, 3 chlorine. Oh, that's not going to work. That's not balanced. So what do? Notice this is 2, this is 3. This is an even odd problem. How do you do that? What number do both 2 and 3 go into to get a whole number? Because the coefficients are always whole number. And how do you do that? Multiply 2 times 3 and 6, because you know they'll divide. So if I want to get 6 chlorine on this side, I'll put a 3 there. So now I have my 6 chlorine. If I want to get 6 chlorine on this side, 3 times 2 there, I'll have my 6 chlorine. And now I have 2 aluminum. Oh, I only have 1 here. How do I get it to 2? And you have 2 aluminum. And now check 2 aluminum, 2 aluminum, 6 chlorine, 6 chlorine. Just, you don't have to do this, but I'll do this. And that's how you do a balanced chemical equation with even odd. And you have this problem set. Now, one question, this should be question 2.
Hey, Professor.
Yep.
For the last one, what do the S and G stand for?
S stands for solid, G stands for gas, and L, if you look down here, stands for, come on, L stands for liquid. And you see that sometimes in a chemical reaction, but for balancing it, ignore it.
Okay, perfect. Thank you.
You're welcome. All questions are good questions. Thank you for your question. This is not only to help you out, but I might have helped some other people out who didn't know that. Now, this one asks, what's the sum of all coefficients for problem this one, I. And I'm not going to give it away because first you got to balance it. But don't forget to do that. And on the next page, we have more, and do them all. Because on test number 2, and I always do this, I usually have, I better say not usually, I will, hold on, let me fix this finger. I will, I will have 4 equations that you will have to balance, 3 points each. So if you don't want to lose 12 points, learn how to do that. If I look at the clock, it's telling me I'm done for today. We did our lab. We did a lot of work together. My back didn't stop me from doing anything yet. I'm in a good mood. And with that, I'm going to say, have a nice rest of the week and weekend. Don't forget, next Tuesday, I'll be doing Chapter 8 problem set, the 3-step multi-problems, weight or mass calculations. And with that, I'm going to say, goodbye. Gay and gesund, be healthy. Back, gay and gesund, get healthy. And with that, I'll see you on Tuesday.